Okay, good morning, students. We are today going to start the analysis of indeterminate structures by flexibility method, element approach. The introductory part of this flexibility method, what is flexibility influence coefficient, how to arrive at the flexibility matrix for a structure based on the structure approach, that is unit load method I have discussed. So we can refer to the previous videos and what is flexibility method. It is derived from the consistent deformation method. The matrix formulation of consistent deformation method is flexibility method. So refer to the previous video on introduction to flexibility method for the introduction to this particular method. Now what I'm going to do today is analysis of structures by element approach. When the size of the structure is very large, we have to split up it into several number of elements. Then viewing the structure as a whole and developing the flexibility matrix by unit load method or any other methods which you have studied in computation of deformations is not that easy. So the necessity for this element approach. By the element approach, we formulate the flexibility matrix using an equation. F is equal to A transpose alpha bar into A, where F is the flexibility matrix. This A matrix is force transformation matrix. Force transformation matrix. We'll discuss how to develop the force transformation matrix. And this alpha bar matrix is called unassembled or uncoupled flexibility matrix. So based on the element approach, we have to formulate the flexibility matrix for the structure. We will be using this equation. F is equal to A transpose alpha bar into A, where A is the transformation matrix, force transformation matrix, alpha bar is the unassembled flexibility matrix. Let us see how to develop these A matrix and alpha matrix. Then you can do the multiplication and arrive at the matrix. Now, what is alpha bar? We have studied or we have derived the element flexibility matrix. Element flexibility matrix. Alpha for a beam element. For a beam element, it is L by 6EI into 2 minus 1 minus 1 2. This is for a beam element. For a bar element or a truss element, the flexibility matrix, the element flexibility matrix is given by L by AE. So these things we have already derived in the previous video. So based on this, I am going to start. Now, what is this alpha bar? So if there is only one element, for one element it is L by 6A into 2 minus 1 minus 1 2. Suppose in the structure there are n number of elements, then this alpha bar or the uncoupled flexibility matrix is obtained by arranging the element flexibility matrices in a diagonal manner. So write alpha 1, alpha 2, etc. up to alpha n. Arrange it in a diagonal manner and all other elements will be 0. So this will be 0, this will be 0. So a matrix obtained by diagonal arrangement of element flexibility matrices is called the uncoupled flexibility matrix. Now what is A? How to develop the force transformation matrix? So that is a real task in this method. If you develop the force transformation matrix correctly, then just by doing this multiplication, we can get the flexibility matrix. This is called a semi-automatic method. There is no general procedure. We have to do a lot of matrix multiplications. Hence, it was not that much preferred as stiffness method. Okay, we'll see how to develop force transformation matrix with the help of an illustrative example. Say structure is given here, a beam ABC, and you are given coordinates. Coordinate 1, a vertical coordinate at point B, and coordinate 2, a vertical coordinate at point 2, point C. So you are asked to develop the force transformation matrix corresponding to the given coordinates. The question is, develop the force transformation matrix corresponding to the given coordinates. So we will be selecting, this is a structure, A, B and C are the 3 nodes. So we can take it as an assembly of 2 elements, A to B, AB one element and BC the second element. So we can treat it as, say, the first element I'll take it as A, the second element BC, I'll call it as small b. The element coordinates are the moments, the bending moment at the 2 ends, P1 of A, P2 of A. So the bending moment at the 2 ends of the elements are the general coordinates for a beam element. This is a nodal force or the nodal coordinate direction. So the global direction is 1 and 2 given in the question. We have to find out what are the element forces P1A and P2A corresponding to each of this load. Now say this is P1 first node. The coordinate, the force at the first node is P1 of element B, that is written at the top. P2, the force at the second node of element B, P1A, P2A, P1B, P2B. Small letters refer element. So this is the element coordinate. Okay, so for the given structure, we split up it into number of elements and take the bending moment at the 2 ends of the elements or the internal moments as the element coordinates. Now, the second step is we have to apply one force at a time. So we apply P1 equal to 1. We apply P1 is equal to unit value. And then you draw the bending moment diagram. Because when we apply P1 equals 1, I have to find out what is the bending moment at this point, what is the bending moment at this point, what are the bending moments at the 2 ends of the element B. A and B, what are the bending moment? So the easiest way is to draw the bending moment diagram. When I give unit load here, you can see with this pen in this direction, in the direction of the load, take moment about this. So this rotates, or the thumb placed like this rotates in the upward direction. Now this bending moment produces, it's a hogging moment. Hogging moment I will draw above the line. So the bending moment diagram for this case is 1 into this distance 3. 1 into 3, 3. This is the bending moment diagram. And this is a hogging moment diagram. This tends to bend the beam up. I'll write here it is hogging. So there's a baseline. I have drawn the baseline with the black ink. The bending moment diagram is drawn above the base. Similarly, in the second case, apply P2 is equal to 1. Apply unit load. P2 is equal to 1. Draw the bending moment diagram. This is the load. Take moment about this point, goes up, or the bending moment diagram is, I have drawn with the blue pen. This is the baseline with P2 is equal to 1. It bends up, or this is also hogging moment. What are the values? Value at this point is 1 into 1, 1. This numerical value at this particular point is 1. The numerical value of bending moment here is 1. The numerical value of bending moment here is 1 into 4, 4. Okay. Now, This is the thing we have to do correctly. With unit load in the coordinate direction 1, draw the bending moment diagram. Unit load in coordinate direction 2, draw the bending moment diagram. Now I am going to write what are the element forces. Force at the first end P1 of element A. Force at the second end of element A, that is P2A. Force at the first end of element B, P1B. Force at the second end of element B, P2B. So I have written P1A, P2A, P1B, P2B. That is equal to, first column will be when I give P1 is equal to 1. When I have given the load value 1 at this coordinate direction, what are the moments? You see here, the bending moment is numerically 3. So I can write P1 of A is 3. Numerically. What about the sign? The sign is from the base to the ordinate. You mark it, this will be anti-clockwise. The moment is anti-clockwise. So it is minus 3. Because our positive sign is clockwise. From the base to the ordinate you measure it. It is anti-clockwise. Thus, at the end 2, the bending moment is 0. For the second element, there is no bending moment value. So it is 0, 0. That is one way to mark it. From the base to the ordinate. Otherwise, what is a hogging moment? A moment which tends to bend the beam up. So it tends to bend the beam up. Here it is positive. Here also it tends to bend the beam up. This is a hogging moment representation. This end it is clockwise. It is 0. At this end it is anti-clockwise 3. That is why I have marked it minus 3. Okay. Now coming to the second, when I apply P2 equal to 1, the moment at this first end is, numerically it is 4. To get the sign, from the base to the ordinate, anti-clockwise. So it is minus 4. At the second end, from the base to the ordinate, this is the ordinate 1. From the base to the ordinate, it is clockwise. So it is plus 1. Here, from the base to the ordinate, minus 1. And here, it is 0. So, I am writing it at the top to make it clear to you. Actually, that shouldn't do P1, P2. That means the total moment at this coordinate direction P1A due to these two together will be minus 3P1 plus minus 4P2. So the bending moment, total bending moment occurring at this point due to this external loads will be minus 3P1 plus minus 4P2. That is called the equilibrium equation. The total moment at this point will be 0 plus 1P2. 0 plus 1. That is written here. 0 P1 plus 1 P2. So that is nothing but an equation connecting the element forces and the nodal forces of the structure. Or I can write it as small p, the element force. This matrix is called the transformation matrix. A into capital P. This is element forces is equal to, this is called, A matrix is called force transformation matrix, or it is also called connection matrix. A matrix which connects between element forces and nodal forces, and capital P is the capital P is nodal forces of the structure. So the relation small p is equal to capital A into capital P. Element forces is equal to force transformation matrix into the nodal forces of the structure. It's a connection matrix. So a matrix which transforms the structural forces into element forces. So which connects between the element forces and structure forces is called the force transformation matrix. It is nothing but the equilibrium equations written in a matrix form. I will illustrate one more example of how to develop the force transformation matrix. Example 2. So the one which we have already discussed is a cantilever beam with coordinates 1 and 2. The second example, it's a simply supported beam. We are given coordinates 1 and 2 to develop the force transformation matrix for this particular case. So here there are, you can take one node here. This is another node. So 1, 2, 3. It is a 3 element structure. So I can mark it as, this is first element, say A. The second element B, and the third element C. The coordinates, this is P1, P2. Similarly here, P1, P2, P1, P2. I have marked the element coordinates, that is all clockwise moments at the two ends, that are called element coordinates. The next step is draw the bending moment diagram corresponding to P1 equals 1. So I will mark the original structure. It's a simply supported beam. Apply P1 equal to 1. At this point, you give unit load. You give P1 equals 1. How to draw the bending moment diagram for simply supported beam? When this load is 1, this distance is 2 meter. This distance is 4 meter. So compute the reactions at these 2 points. What is the reaction here? 1 into 4 by 6. So this reaction will be 4 by 6. This reaction will be 2 by 6. 1 into 2 by 6. Now to draw the bending moment diagram, at this point, the bending moment here is 0. At this point, the bending moment will be load into distance, 4 by 6 into 2. What will be the value? 4 by 6 into 2. This is the direction of the reaction. Take moment about this, it comes in clockwise direction. So it comes below the line. With reference to this, take moment about this, clockwise direction. So the line has to come down. 4 by 6 into 2. This will be 8 by 6. From this, 2 by 6 into 4, that also 8 by 6. So this is the bending moment diagram when a unit load is acting. So this is called a sagging moment. That is a sagging moment. Here it comes clockwise, tends to bend the beam upwards, downwards. 2 by 6 into 4, this tends anti-clockwise. So this is a sagging moment. So this bending moment diagram is drawn below the line. Next case, apply P2 is equal to 1. Apply P2 is equal to 1. Apply unit load here. So this distance is 4 meter. This distance is 2 meter. It's a simply supported beam. So what is the reaction here? The reaction at point A will be 1 into 2. 2 by 6. Reaction at this point will be 1 into 4. 4 by 6. So these are the reactions. To draw the bending moment diagram, the bending moment at this point is 0. Bending moment at this point will be 2 by 6 into 4. This is 8 by 6. 4 by 6 into 2. That's also 8 by 6. It's a straight line. So this is the bending moment diagram. So this is easy for you, how to draw the bending moment diagram. So it's a sagging moment. I have drawn it below the line. So this is the bending moment diagram. Now I have to write I have to compute what are the bending moment corresponding to this point here, here, everywhere. So this is one node. Another node is here. So I have to find out what is the ordinate here. The ordinate at this point will be 2 by 6 into 2, or from the symmetry of this 8 by 6 upon a distance of 4. So what will be this? 2 by 6 into 4, this will be 4 by 6. This ordinate is 4 by 6. Similarly, in this diagram, this is the corresponding to node 2. So corresponding to this, I have to find out what is the ordinate. This ordinate will be 2 by 6 into 2. This is 4 by 6. Or from the similarity of triangles, 8 by 6 upon a distance 4. So what will be on 2? Either by similar triangles or by directly taking moment, you can find out the bending moment at those 2 points. Now I am going to write. We have 3 elements here. P1 of A, P2 of A. Okay. Then P1 of B, P2 of B. Then P1 of C and P2 of C. The bending moment at the 2 ends of the elements is equal to, by giving P1 is equal to 1, you write down what are the values. P1, when we give P1 equals 1, what are the values? The left edge, this point, P1 of A is 0. P2 of A is, numerically it is 8 by 6. What about the sign? From the base to the ordinate, you draw this arrow. Base and then the ordinate later. It is anti-clockwise. So it is minus 8 by 6. Then for the second element, B, the first 10, the moment is, it is numerically 8 by 6. What about the sign? From the base to the ordinate, clockwise. So it is plus. Now here, P2 of B, this is P2 of B. From the base to the ordinate, it is anti-clockwise, minus 4 by 6. For the third element, from the base to the ordinate, it is plus 4 by 6. And here it is 0. So by giving P1 is equal to 1, the bending moment at this point is 0. This bending moment is minus 8 by 6. For the second element, it is plus 8 by 6 and minus 4 by 6. For the third element, it is 4 by 6. 0. It is written. Similarly, when P2 is equal to 1, by giving P2 is equal to 1, what are the values? First node, it is 0. At the second point, it is from the base to the minus 4 by 6. For the second element, it is plus 4 by 6 and minus 8 by 6. For the third element, it is plus 8 by 6 and 0. So that into P1, P2. So this is of the form P is equal to A star P. So this is the force transformation matrix of the structure for the given coordinates.